I just want to run through a quick example where we use the extreme value theorem to find the absolute max and absolute min of a function, in this case capital F of x, on an interval, a closed interval. For us that's 0.5 and 2. Like I said, we're going to use the extreme value theorem. And essentially this thing tells us where to look. We're going to look at endpoints and at critical points. The endpoints are easy to identify. We're going to see what the function value is when we plug in 0.5, and we're going to see what the function value is when we plug in 2. The other thing we need to do is find the critical points. And to do that, we have to examine the derivative. So let's get a blank screen and we'll go ahead and do that. So I've rewritten the function and the closed interval here. What we need to do is take a look at what's happening with the derivative. There are two things that we need to check after we compute the derivative. Let's do that first. Let's see, I'm going to bring the negative 2 down, makes a positive 2, and that'll be x to the negative 3. The derivative is 2 over x cubed. Once you have the derivative, you're looking for places where this derivative is equal to 0 or where it's undefined. So you want to solve this equation. 2x cubed equals 0. And the result is that there's no solution. There's no way to make 2 over x cubed. I said 2x cubed, but I meant 2 over x cubed. There's no way to make that 0. So there's no solution here, meaning there's no critical points where the derivative is 0. Is there anywhere where 2 over x cubed is undefined? And yes, there is. X equals 0, right? That 0 can't be in the denominator. Here's the thing. 0 is not a part of this closed interval. So we don't worry about this one either. The only points that we have to check are 0.5 and 2, the endpoints. There are no critical points for this function. So let's find out which one's the min and which one's the max. To wrap this problem up, we just need to find out where our absolute extreme values are. When you plug 0.5 into f, essentially what you get is negative 1 over 1/2 squared, right? 0.5 is 1/2. And that turns into negative 4. How's that look? And when you plug a 2 in here, you get negative 1 over 2 squared, which is negative 1/4. So I'm going to say that this is an absolute min. We'll call that an ABS min for short. And this is an absolute max, because 1/4 is higher, negative 1/4 is higher than negative 4. We're supposed to show a quick graph of this in the problem to make sure. I'm going to cheat, and on the next slide I'll show you what I get when I plug these bad boys into Desmos. So as you can see, I've graphed the function negative 1 over x squared, and the way you add a closed interval for the domain is simply next to it you put the interval with inequality notation in curly braces. So please remember to use the curly braces if you ever want to add an interval on your graph. And so what we see is that in fact we do have that y value, a max, which is about negative 1/4. Oh my goodness, that doesn't look like 1/4. And down here we have that negative 4. So I use Desmos just to show a graph. It does verify what we found out using the extreme value theorem. Hopefully this helped. I know this function was weird because there weren't actually any critical points, we just had the endpoints. But that's the idea. You test the derivative, look for places where it's 0 and places where it's undefined, and those values have to be in the domain, otherwise they're not useful to us. Good luck. I'll see you soon.